Sometimes I feel alone, you know it's me and my guitar. We're looking up at all them stars, singing where we supposed to go now. Ruthie, little lady, tell me what you mean to me. And I'll build a house in Byron Bay, if that's exactly where you'll be. I'm coming home, put a flower in your hair. But you should know
Ladies and gentlemen, welcome to the session on applications. My name is Hans-Peter Nehe, and I'm at the KTH Royal Institute of Technology. We have 5 presentations. One of them, the third one, is a recorded one, and that's 28 minutes long. So I would like to ask the presenters to stick to the timeline, preferably to be a little bit shorter. The first one out is Per Ranstad, who works at the Linnaeus University and at Solutions for Tomorrow. He will give a presentation about silicon carbide polytronics in mobile X-ray equipment. The floor is yours.
Thank you. So, I will tell a little bit about a project which has been running for 2 years now. And it's to see what to investigate the benefits we can gain in a mobile X-ray equipment by using silicon carbide Mosfets. And it's a cooperation between KTH, LNU, and Solutions for Tomorrow, which is a company having this as a product. And the project has been co-financed by Swedish Energy Agency and Mistra Innovation. So this picture displays what this system looks like. You can see it's an interior from a hospital. It's actually not, but it tries to look like that. So the machine is on the left-hand side, where you at the top here, you have the X-ray tube. So basically you have the camera here. And here is the power generator and computers and a battery, because this is battery driven, and that is one of the drivers for having silicon carbide power semiconductors and have low losses so that we can have a smaller battery or use it for longer time. And you also have so here you see the screen where you can see the images. And so the target for the project, that is to reduce losses, improve the energy efficiency, and do that by using silicon carbide components. Today is used IGBTs, silicon IGBTs, and also to minimize losses by work a little bit on the topology. Another main target, that is to reduce size. That means a higher power density, because it's movable. The smaller the better. And that goes with higher switching frequencies, which gives smaller reactive elements, and we can make a much smaller generator. And third one is related to the quality of the images. And that is we can achieve that if we can have faster rise and fall times of the X-ray pulses, because that means that we can have faster pictures, and they are going to be sharper. This project has also resulted in at least 2 publications at the last EPE. One on circuit analysis and one on basically applying SiC MOSFET into this topology, which is a quite odd one, I would say. And the outline of the presentation here is to look into main circuit, do the analysis of the circuit, show some test results, and have a discussion at the end. So here you see the main circuit of the power generator. You have the voltage source on the left-hand side. That's the battery. Typically, no load voltage of the battery is in the range of 340 volt. Once loaded, it goes down below 300. There is a transformer you see in the middle, which transforms the battery voltage up to something like 100 kilovolt. Doesn't take the full step in the transformer. There's also a voltage doubler in the rectifier. And a typical voltage pulse is 100 kV, 32 kilowatts, and it lasts for in the range of 100 milliseconds. Of course, there are many variations of that, but that could be a typical one. And the switching frequency is 25 kilohertz using a PWM, pulse width modulation, for control. One interesting thing might be here that you see the bridge, IGBT bridge on the left-hand side, and you see the transformer in the middle. And between there you have a network of 2 inductors and a capacitor. All of those are parasitics of the transformer. So the transformer has been tuned to carry the main elements as parasitic components, which makes it a little bit difficult to change the topology should you want to do that. First step here was to identify these parasitic elements and make a simulation model so that we can see that we understand what the system behaves like. And you can see here it might be not too easy to see, but the purple trace here, that is the main current. That's the current coming out of the, going into the primary of the, going out of the IGBT bridge into this inductance here. And then we built a circuit model and run simulation and tuned the model. So here you see the red dotted line here is actually this one. So that is a measured wave shape. And the blue line is a simulated wave shape. So it's fairly spot on, which tells us, and we can measure different operating points and compare to measurements. So we have a good match. So we have a good simulation model, circuit simulator to judge the operations. One key thing is to judge what is the status of the present system, having IGBT modules, half-bridge modules, as main switches, and which is the performance of that. So thermal losses has been partly measured and partly calculated. So we measure the voltage, basically the current waveform, and calculated RMS and average current out of that, and from that we get the conduction losses. The switching losses we are measuring from the wave shapes here, so the rise of the voltage and the fall of the current, and calculating the oscilloscope. And this ends up in an estimate of the losses to slightly below 3 kilowatts, which indicates 10% losses in the IGBTs, which is quite high. And it's you can see, for example, here, this, which looks like a little bump. That is the impact from the parasitic inductance of the power loop. And this is actually measured on the terminals of the IGBTs. If you go inside here, it is way higher. It's almost clamping to 650 volts. And that is what dominates the switching losses. Based on this, we built a physical test system to be able to, in pulse mode, measure evaluate the total system losses and be able to test with different switches, namely silicon IGBTs and silicon carbide Mosfets. And since this system is designed to operate in a pulse mode, it cannot operate continuously. It will burn within 1 or 2 seconds. It is not designed to have a continuous operation. So what we did here is that we did build the system here, like what I showed in the main circuit diagram. With the difference that we don't have here a high voltage transformer. It's a transformer with a turns ratio between primary and secondary, which is roughly 0.7. That means that if you have 200 volts here, you will have 140 volts here. So the circuit will see 70% of the output voltage. And that is quite typical for this 100 kV pulse. But what this enables is that we can choose to have the same output voltage as we have input voltage, meaning that we can just recirculate the output power to the input. So the generator loads itself. And that means also that what comes here, that is only the losses. So we can directly measure the losses. And we do it with having a capacitor here, which is charged to a certain voltage, 200 volt, 250 volts. And that is from a low power voltage source. Then we open this switch, so we are not connected, and then we run a pulse. And then we can just measure how much voltage did the capacitor lose during the pulse. And from that we have the energy, and then we have the power loss. So that has been a quite efficient system to just be able to measure fairly accurate the losses in a pulse mode. So, and here we have a first test we did on what will SiC MOSFETs bring. We had roughly 2.7 kilowatts from the silicon IGBTs, and that was we could reduce the losses of the switches by roughly 1 kilowatt. But if you then calculate, that means that try to calculate the losses what you would expect in the SiC MOSFETs. This is way more. Might be 3 times the expected value. So there is still more than 1 kilowatt of switching losses, which you shouldn't have in a SiC MOSFET. So when I analyze, this goes back to the parasitic inductance, both of the module and of the main circuit. So I'll give you some examples. It's not exactly the same circuit, but let's discuss a little bit. Here's a measurement we did in a similar project some years ago, where we actually have here you can see a capacitive snubber, and we have the parasitic inductances here in this loop. And this is the switch current here at the turnoff, and this is the voltage across the switch. And this is actually the current of this capacitance. But what you see here, it's not very easy to see, but you see a lot of oscillations here, and you see the charge to charge this capacitance from 0 to until this diode opens. But you can also see a quite high pulse here during the actual turn-off of the IGBT, and that is a result of this inductance in this loop inductance here. So when current is decreasing here, you will induce a voltage here, which will come across the switch. And if you simulate it and expand the scale a little bit and simplify so that you don't have the output capacitance of the switch in the circuit, you'll see it like this. So the blue curve here, that is actually the voltage across the capacitance. In this case, quite low. And this curve here, that is the induced voltage of these inductances, and that one is way higher. So this is, and the sum of these two voltages, namely this one, is what appears across the switch during the fall of the current. So this one is what gives the turn-off loss, together, of course, with the fall time here. And if you analyze this, you'll see that the energy given by this rectangle here equals the energy stored in the inductance. So the value of the inductance just gives you the turn-off losses, at least the dominating parts. So a very important takeaway so far was that we can't use modules because they have way too high inductance. We cannot make it low loss at high frequency. Here are some measurements where we compared modules. This is a SiC Mosfet module, this one here, which has, will not take too long to explain these numbers, but the higher the better. That is some sort of a figure of merit which has a dimension of frequency. The higher the better. So you see for this type of module, it's 82 kilohertz. We can have a better module, lower inductance, and you get a number. It's 5 times better. But we can also go discrete. And here it's just through-hole mounted. If we go surface mount, it's become even lower. And this number here is now a factor of 20. Yes. So basically, with this component here, we can operate with a switching frequency which is 20 times higher, having the same relative losses. That is how to understand it. So in this case, in this application, the circuit parasitic inductance of the switch together with the parasitic inductance of the power loop is a killer. We need to minimize those. So these are the takeaways. So in order to meet these project targets, which is, we can meet all of them if we can have very high energy efficiency at a high switching speed. That meets all and enables us to meet all the targets. And that calls for very low inductive packaging, points to discrete devices, minimize parasitics in the power loop, PCB-based design. Once we have low inductances, we can switch very fast, and by that also lower the switching losses. And as a fourth point, we can look into topologies, which allows for soft switching, not hard switching, which is in the present design. And thanks.
Okay, any questions?
Yes?
Modules you have shown 51 nanohenry and
Yes.
something.
Yes.
Is it only the module itself, or you have the total stray inductance in the commutation loop?
It is only in the module itself, and it's from the AC connection to either plus or minus. Normally, okay, if you go plus to minus, it's lower because they have a much lower area.
Okay, thank you.
So in general, the total inductance in this application is coming close to 100 nanohenries, so it's very high. But at least 1/3 of that is inside the module.
Okay, we have time for one more question. Okay, it seems we don't have any more questions, so let us thank Per Arnstad once again. Our next speaker is Mats Vårdemark from Powerbox, and he will talk about use of silicon carbide MOSFETs in DC-DC converters. The floor is yours.
Thank you. Thank you. I will give you a presentation from a design perspective. And Powerbox is a Swedish company founded almost 50 years ago, working with design of power supplies. Now we are in the right picture. Powerbox design DC-DC converters in a power range between roughly 200 and 5,000 watts. And in a voltage range between 12 and 2,000 volt. So it's a quite wide range of products. The applications will mainly be railway, industrial, medical applications. We have worked with silicon MOSFETs for a very, very long time. Sometimes IGBTs, but mostly MOSFETs. And we see in the future that we will continue with silicon, but for sure also add silicon carbide MOSFETs in our products. We are today somewhere in between, that we're working with silicon carbide technology to learn the technology. And what we need to learn is how to use the new components and when to use the new components. And maybe the last question here, why to use silicon carbide, is a stupid question, but I would say more, should we use silicon carbide or should we use silicon or should we use something else? And that will be dependent of the application, a lot depending on voltage range and power range. We have seen here today that a lot of companies working with new components and new technology, and the technology will be developed all the time. And as a design engineer, we like that a lot. We want to follow the development of new components and use the new components to, in the end, have better products for our customers. And it's a lot related to reduce the power losses. As a design group, I'm presenting, we follow the development of components. There we have some of the companies working with development of silicon carbide components. We also got a lot of information of good things and benefits with silicon carbide, like lower on resistance, lower switching losses, the increase of the on resistance versus temperature is a very important thing. Eliminating tail current during switching, low capacitance, low gate charge. All those things are good things, important things, but we also have to learn about how will it be in comparison with, for instance, the silicon MOSFETs we use today. And we are back then, how to use the silicon carbide MOSFETs, when to use them, and again, Should we use silicon carbide or should we use silicon or something else? How to use silicon carbide MOSFETs is one very important thing for us as a designer for a power supply will be the gate drive technology. That will be fundamental to be effective, and that's needed to reduce the losses. From a power supply perspective, it's also important that it works in all different conditions during startup, short circuits, that it gives a reliable product in the end. In that area, we have done investigations of different drive circuits and used them together with different silicon carbide MOSFETs. There we have used double pulse tester for investigation of turning on, turning off capabilities. And we have learned a lot from that. We have also used and investigate different drive circuits in our existing products together with silicon carbide MOSFETs. And there we also have added the switching frequency as an important parameter to learn and know what will be the optimal switching frequency. When we talk about when to use silicon carbide MOSFETs, we work mostly in the area of 600, for silicon carbide, 650 volt up to 700 volt or maybe more 1200 volt will be the types we will use. Those silicon carbide MOSFETs we can use them in AC/DC converters, single phase or three phase. And we can also use them in applications that we have high voltage DC/DC converters. We compare the results with silicon MOSFETs. There are also development in the silicon area. And yeah, we follow that as well to, in the end, find the best solutions and find the best solutions for our customers. We have seen, of course, that high power applications, and then what is high power application? For us, it may be around 1 kilowatt and up. And there, of course, the benefits with silicon carbide will be more significant. Short example, lowest there. What can you win if you increase the efficiency with 2%? Of course, we can win more there if we have a higher power level. So we compare different types. This is maybe not the newest types, but those types are available at the market. We can see that RDS on for a silicon carbide MOSFET is 10% of the device of silicon. And here we also should remember that the RDS on, this is at room temperature, the typical value. For instance, for a power supply, for a railway applications, that one have to give full power at the ambient temperature of 70 degrees. So there we are in the range of 100 or a little bit above 100 degrees at the semiconductors. And the difference there will be even larger at that temperatures. So here we can see that the silicon carbide MOSFETs have very large benefits in that range. And as we have heard today before, that we can't just compare cost of the silicon carbide MOSFET compared with the silicon MOSFET. In a power supply we are working with, there will the mechanical part and the heat sinks to handle the power losses be a very big part of the total product cost. And if we can improve and reduce the power losses, I would say that the cost for the heat sinks and for the mechanical stuffs will be, you can say more there compared with the extra cost of silicon carbide. Another comparison, we have a product range which use silicon MOSFETs in around 200 volt, 250 volt. It's an area there are not a lot of development of new devices. We compare, can it be possible to use silicon carbide instead? But here we can see that no, the RDS-on will be higher and the cost will be higher, so we will not win a lot of efficiency there. So this will be an application there we don't go for a silicon carbide. And then finally the summary of why to use silicon carbide, or should we use silicon carbide or should we use silicon? In higher power products, there is more easy to see that, okay, here silicon carbide have a lot of benefits and we can win a lot, we can reduce the losses a lot. So there it will be quite simple. Then of course there will be some gray zone in between. There it maybe needs more investigations to finally select if we go further with silicon or silicon carbide. But as I mentioned, the big benefits is to reduce the size of heat sinks, and that will also reduce the product cost. The reduce of the size for the heat sinks will also give a more compact design, a compact product, and in some ways that can be very important for our customers. The improvements in efficiency will also give lower cost for energy for the customer. That can also be an important part. And the cost for the energy increases. If you have a lot of power losses, you have to cool down everything, and that costs a lot for the customer. And we will also win if we can reduce the size regarding transportation of those stuffs, and this gives a more environmental friendly product in the end. So that's a little bit of a picture of, from a design perspective, from the design group I'm presenting. We are full of the development, and we are very happy that there is a lot of ongoing activities that help us a lot to finally design good products. That's all from me. Thank you.
Thank you very much. Do we have any questions? Yes?
Thank you. In the slide 10, you have compared 200 volt with the 650 volt device, and then you have reached this conclusion that you, for some of the application, you're not going to switch to SiC. Could you explain that one, why you have compared these two devices? Haven't you found the silicon carbide with a lower breakdown voltage, or?
No, we haven't found that. We found the available 650 volt. We know that they are quite good, but you can't replace them with a 200 volt silicon Mosfet. That's what I mean. We're looking for silicon Mosfets in that range with low RDS on. Maybe we can use silicon carbide, but our investigation shows that that will not work well.
Due to that there are so many GaN devices in that range of the voltage,
Yeah.
don't you think it's more suitable to switch for that application to the GaN?
Yeah, I think so. Yes.
Good. Thank you.
Yeah.
What do you think, how is EMC perspective when you compare between silicon and silicon carbide? What do you think? How much is the difference? How much effort do we need to put to control the EMC?
We haven't done so much of investigations, but we expect a similar or better result for silicon carbide because of the switching characteristics for the silicon carbide MOSFETs.
Thank you.
I noticed that you didn't mention gallium nitride, which would be natural to compare with silicon at those low voltage levels. Then I think that you didn't find low voltage MOSFETs in silicon carbide. It depends that the resistivity in the substrates is such that there is no point of doing probably lower voltage MOSFETs because you don't gain so much on the in resistance anymore.
Yeah, this presentation was a little bit in direction to silicon carbide. Of course, we also follow what's going on in the GaN, and maybe we can come back next year or in 2 years to present that.
So, any additional questions?
Yes, of course. Yes, we follow all trends. Yes, yeah.
I have a question. Thanks for the presentation. My question is It's not on? Okay, now it's on. My question is, you tell your customers that by using silicon carbide, they're going to be saving energy over the life of the system, correct? So my question is, are people willing to pay more money up front with the prospect of saving over a number of years and coming ahead? Or do they look for an equal cost between silicon and silicon carbide solutions? So are they willing to pay for that, to pay more for that energy savings? What is your experience talking to customers?
Yeah, we have that experience that there will be customers which will pay a little bit extra for the product and looking more of the lifetime of the product, and if they can save energy costs there, then it's possible for them to pay extra for when they purchase a product.
And when you sell a product, do you offer the life of system cost to the customer, or do you just focus on the, price itself up front? What is the way you approach selling?
Yeah, the experience there is that it's still a focus of the product price, but I think that will be changed in the near future. to looking more into the complete cost.
I think that's the right approach too. It's just a question of the customers, you know, agreeing with that, right?
Yeah, yeah, I agree. Yeah.
Thank you.
Thanks.
Thank you very much. Let us thank the speaker. Our next presentation is made by Shibo Yuan from University of Bristol, and this presentation is recorded.
Hello everyone, this is Shibo Yuan. It's my pleasure to talk about our work on the motor winding and bearing stress under fast-switching wide-bandgap devices and their mitigation strategies. So actually it's quite a big topic to be covered in 20 minutes. But you can look out for our publications where you can find more details about our work. The fast switching speed, hard switching frequency of wide bandgap power devices have brought in clear opportunities in achieving high density, high efficiency, high frequency, and highly integrated motor drives. However, the high frequency switching can also negatively impact electrical machines in terms of motor overvoltage, insulation and bearing degradation, and electromagnetic interference. So today, I will talk about the opportunities, challenges, and some potential solutions with the wide bandgap motor drives. The superior characteristics of wide bandgap material has really offered high switching speed, high voltage, and high temperature operation capabilities for the silicon carbide and gallium nitride devices. So there are devices with various currents and voltage ratings on the market, and the silicon carbide devices are normally rated above 650 volts for high voltage applications, and the gallium nitride HEMTs are normally rated below 650 volts, targeted for lower voltage applications. So this slide shows the experimental test for high power modules, both the silicon carbide Mosfet modules and the silicon IGBT modules. As you can see that the silicon carbide Mosfet can turn on and turn off very fast, generally within 70 nanoseconds, but the silicon IGBT ones has a much longer turn on and turn off time, and you can also see the clear tail current during the turn off. These are the tests for the 1700 volts, 300 amp modules. So as we all know that for silicon IGBT based hard switching converters, the switching frequency are normally below 20 kilohertz and with the efficiency around 98.5%. But with the fastest switching silicon carbide MOSFET, this switching frequency can be extended to 40 kilohertz or even higher. So this high switching frequency capability can help to reduce the harmonics-induced losses, reduce filtering components, including both the AC side inductors and the DC link caps, and also it can enable high fundamental frequency drives where you have a high speed, high number of poles for the electrical machines. This slide shows a gallium nitride-based three-phase DC to AC inverter. As you can see that the gallium nitride devices can finish a switching transition within 10 nanoseconds, very fast switching. And here we have also demonstrated 3 kilowatt, 300 kilohertz operation of that DC to AC converter, and the DC link voltage is 400 volts. So the wide bandgap devices has benefits the motor drives in various applications. For example, in this application, the high switching frequency can help to reduce the rotor magnet losses, which help to solve the heat and loss dissipation issues. And also it's well known that the Tesla Model 3 EVs using 24,650 volt silicon carbide MOSFET in their inverters. So I will talk about the opportunities for silicon carbide and gallium nitride based motor drives. There are also challenges related to the fast switching speed and high switching frequency. So one of the main challenges is the motor over voltage due to the high frequency operation. So this is not a new thing. Even in silicon IGBT based converters, you will see high over voltage at the motor terminal if there is a long cable between the inverter and the machine. But for silicon carbide converter with very fast switching, even a short cable can lead to over voltage at the motor terminal. So in this case, we have shown you a 1.6 meter cable length, and where you can see here, the inverter output voltage is 600 watts, but the motor terminal voltage has reached 900 watts, almost 50% over voltage. So this slide shows the motor over voltage with respect to the cable length under various switching speed. So for example, for a writing time of 25 nanoseconds, which is a typical silicon carbide Mosfet switching speed, with about 3 or 4 meters of cable, you will have a double voltage at the motor terminal, which means the motor terminal voltage is twice of the inverter output voltage with only 3 or 4 meter cable length. And the motor terminal over voltage can even be higher than double. In this case, the inverter output voltage is only 50 watts, but the motor terminal voltage has reached 135 watts, even higher than double the inverter output voltage. So this happens because the switching instance of the inverter output voltage are very closely spaced. We call this the double pulsing effect. Basically, the two pulses are too close to each other. This happens when you have a high switching frequency and also the modulation index is high. So I will summarize, there are 3 types of motor over voltages. At the motor terminal, there are 2 types of over voltage. That is a differential mode over voltage. That is the phase-to-phase or the line voltage. And there is also the motor terminal common mode over voltage. That is the phase to ground over voltage. And then there is a 3rd type of over voltage. That's the motor neutral over voltage. That's the common mode type of over voltage. You will see an over voltage at the motor stator winding neutral with respect to the ground. So we have demonstrated this in experiments. So for example, this one shows the motor terminal differential mode over voltage, where the green trace is the motor terminal phase-to-phase voltage, and the yellow one is the inverter output voltage. And this one shows the motor terminal common mode over voltage, and the green one is the motor terminal voltage, and the yellow one again is the inverter output voltage. So you can analyze this over voltage and oscillation phenomena in both the time domain and the frequency domain. In the time domain, you can use the so-called bouncing diagram to analyze that. And the conclusion is the oscillation frequency of this over voltage equals 1/4 times Tp, with Tp being the traveling time of the wave along the cable. Okay, so you can work out the oscillation frequency by knowing the cable length and also the traveling speed of the wave. You can also analyze this phenomenon in the frequency domain. Basically, if you measure the impedance of your cable, and then you can find out the anti-resonant frequency, and this oscillation frequency will be the same as this anti-resonant frequency, because the impedance at this frequency is so small, and then the harmonics will trigger an oscillation at this frequency. Let's look at the switching frequency effect and see how the over voltage varies with different switching frequencies. First, we look at 10 kilohertz, and again, this red wave, these green waveforms are the motor terminal voltage, and the yellow one is the inverter output voltage, and the blue one is the motor current. As you can see, the motor terminal voltage is about twice of the inverter output voltage. And then if the switching frequency is increased to 50 kilohertz, and then we have the motor terminal voltage even higher than twice of the inverter output voltage. And if we further increase the switching frequency to 225 kilohertz, and you can see that the motor terminal voltage is almost 4 times of the inverter output voltage. The reason is that the double of the switching frequency coincide with the anti-resonant frequency of that cable impedance. So this causes a very high overvoltage if you select a switching frequency where itself or its multiples coincide with the anti-resonant frequency of the cable. And then let's look at the motor stator winding neutral point overvoltage. This is a common mode type of overvoltage because of the impedance mismatch at the motor stator neutral. And we can analyze this using the space vector diagram. Basically, if you know the two-level converter modulation, you will know there are 8 space vectors, and there will be corresponding common mode voltage associated with these space vectors. And for the 2 zero vectors, they have the highest common mode voltage, and they are going to generate the most overshoot. So at low modulation indexes, you will use more zero vectors. And then the common mode voltage is highest, then you will have the most of the overshoot at the low modulation index. And when the modulation index is high, this overshoot will be smaller. But please pay attention to the anti-resonant point of the motor common mode impedance. Again, there is the anti-resonant point. And if your switching frequency coincides with this anti-resonant frequency of the common mode impedance of the machine, then you will have a huge overvoltage at the motor stator neutral. In this case, the frequency is 53 kilohertz. And this overvoltage, these 3 types of motor overvoltage does not drop equally on all the turns or all the coils. They normally drop on the first several turns of the winding. So the first several turns of the winding are most stressed. Okay, so that means the first several turns of the motor terminal and also the last several turns close to the motor neutral, you will have the most stressed turns. So their insulations will be stressed more than others. So this overvoltage will cause the winding insulation degradation through the partial discharge effect. Basically, if the voltage is higher than the partial discharge inception voltage, it will trigger a partial discharge. And this partial discharge effect will eat up some of the insulation material, and over time, it will cause the insulation breakdown. In order to analyze what kind of waveforms will trigger a PD, that is partial discharge, you can use the so-called field change diagram to analyze that. For example, these 2 waveforms, so the one on the left will have more chances to trigger a PD because first, its magnitude is higher than the partial discharge inception voltage. Another important reason is because it has a high voltage change delta wave. Okay, so this voltage change or voltage jump has really caused the PD events. And similarly, you can use this field change diagram to analyze a two-level waveform, switch waveform, where this black one shows. And the PD normally happens when you change the polarity of the voltage, for example, from the negative to the positive, or from the positive to the negative. It will have the PD events. And also the high switching frequency of wide-bandgap motor drives also means more frequent PD occurrence, because you have more pulses within a certain time under high switching frequencies. So you can also use that to analyze a three-level PWM. Generally speaking, you will get less PD events for a multi-level waveform, because the dVdt, the delta wave, is smaller. And we have measured the partial discharge events in experiment with a silicon carbide converter driving twisted pair. And we have detected the PD events and put that in the phase diagram with the voltage waveforms. For example, this is with a two-level converter without any cable connected between the inverter and the twisted pair. You can see there are only PD events, partial discharge events, when the polarity of the pulses changes from negative to positive or from positive to negative. And if there is a cable between the inverter and the twisted pair, then there will be over voltage at the twisted pair. And as you can see, there will be more PD events almost at every switching transition. So we have also tested that for three-level converter. Again, the PD events occurs during the polarity change. And if you have a higher voltage, then you will get more PD events. We have also tested several motor rats. That is a motor stator winding with a core. And there are 9 samples. And they are driven by silicon carbide inverters under 3 different types of DC link voltages. That is 600 volts, 800 volts, and 1000 volts. 3 different switching frequencies, 20 kilohertz, 40 kilohertz, and 60 kilohertz, and also different driving times. And basically, high DC link voltage and high switching frequency will clearly reduce the lifetime of the motor rest or the motor stator windings. So another effect due to high-speed switching is the motor bearing degradation. And as an indication, people normally use the bearing current to indicate how the fast switching will degrade the motor bearings. And for smaller machines, there are 2 types of bearing current. That is the EDM type of current and the dVdt current. And the magnitude of EDM current is much higher than the dVdt current. And the EDM current will cause more damage. And we can set up a system to measure the bearing current by passing the current originally going through the bearing. Now we can force the current to go through another wire, and then we can measure the bearing current here. And here is a comparison between a silicon IGBT based inverter and a silicon carbide Mosfet inverter for the bearing current. As you can see that with a silicon carbide a Mosfet inverter with much higher switching frequency and switching speed, the bearing current is much higher than the silicon IGBT based converter. And we have tested the bearing current under the switching frequencies from 10 kilohertz to 100 kilohertz. And as you can see that under 10 kilohertz, most waveforms looks as predicted, where there are 4 voltage levels in the common mode voltage or the neutral to ground voltage. But this has turned to a most sinusoidal-like waveforms. And there will be also more oscillations in the bearing voltage and the bearing current. And we have measured the dV/dt type of current, which is basically a capacitive type of current, and also counted the occurrence of the EDM current. As you can see that with the increase of the switching speed, there will be higher dV/dt current because it's a capacitive type of current. With high dV/dt, you will have more capacitive current. And the EDM current count does not change much with the change of the switching speed. And then we see the impact of switching frequency. With switching frequency rising from 10 kilohertz to 100 kilohertz, as you can see, the dV/dt type of current will increase due to the oscillations in the bearing current. But the EDM-based current will increase first and then goes down a bit. It increases first because it's high switching frequency, then there will be more high voltage chances, which will trigger more EDM events. But with the switching frequency goes even higher, then the duration of the high voltage at each pulse will be smaller. Then it will not trigger the EDM events. That's why the number has reduced. Next, I will talk about some potential solutions in wide-bandgap motor drives to deal with the over voltages and other effects. So the most used solutions is passive solutions where you use filters. For example, you can add the filters at the motor terminal where you can match the impedance of the cable and the machine side. Then there will be less motor over voltage. And you can also use various other types of filters, for example, the dV/dt filter and the sinusoidal filter, where you can remove all the harmonics and then you can reduce the voltage overshoot of the machine. In addition to the passive filters, where under high current conditions, the passive filter can be very big, lossy, and also can be high cost in some applications. Then we can look at the active solutions. Here I show you the two active solutions of multi-level converters and soft switching converters. So basically, wide-bandgap devices have achieved very low switching loss by having very fast switching speed, but it increases the dV/dt, the EMI, and the harmonics as a side effect or as a negative effect. But the multi-level converter, as you can see here, because it has more voltage steps, so it can reduce the dV/dt and harmonics. And also because in a multi-level converter, each switching device only switch a portion of the DC link voltage. So the switching loss is also low. So the multi-level converter can achieve a low switching loss and a low EMI at the same time. And also for the soft switching, because the voltage and the current are decoupled, so it has low switching loss. And also because the resonance nature of the switching transient, then the output voltage shape is smoothed. So the dV/dt and also the high order harmonics are reduced. So the soft switching can also achieve low switching loss and EMI at the same time. So this slide shows you the comparison between a multi-level converter and a two-level converter under hard switching. And on the left is the two-level hard switching converter, and the blue waveform is the inverter output voltage, and the purple-ish waveform is the motor terminal voltage. As you can see that there is clear over voltage at the motor terminal. And on the right is the three-level converter waveform. And as you can see, the over voltage is half or is smaller than the two-level case because the delta V or the voltage change is smaller for the three-level converter. And then for the soft switching, we compare it with the hard switching. And for the hard switching, you can see that the green one is the motor terminal voltage, and the yellow one is the inverter output voltage, and the motor over voltage occurs here because it's a hard switching. And for the soft switching, we can shape the switching edge of the output voltage waveform during the output voltage transition, and then we can eliminate the voltage overshoot at the motor terminal as shown here. So basically, how to set the rising or falling time of the soft switching converter. So I show you here, if you set the rise time of the soft switching converter output voltage, then to be 4 times of the traveling wave time along the cable, then you can eliminate the voltage overshoot. And of course, at other times, for example, the 8 times of the traveling time along the cable, you can also remove the terminal over voltage. There are other ways to reduce the over voltage. For example, we can use something called the quasi multi-level PWM, where this is standard switching edge. And if you insert a short time duration, here create a third level, and it can help to eliminate the reflected wave and or cancel the reflected wave. Then you can remove the voltage overshoot at the motor terminal. And here I show you the experimental results where if you use a quasi 3-level PWM, you can remove the voltage overshoot at the motor terminal. There are other types of converter topologies. For example, this one have an embedded DVDT filter in the circuit, which helps to reduce the voltage overshoot and also reduce the harmonics in the current due to the capacitance charging of the cable. So I think it's a good time to summarize. The high-frequency wide-bandgap device-based motor drives can bring in clear opportunities for improving the system performance. However, the high switching speed and the high switching frequency will cause 3 types of motor over voltages, and the potential consequent stress to insulation and bearing health has been presented. So passive or active solutions altogether should be considered to mitigate the negative side effects in wide-bandgap motor drives. And also, you need to take a systematic approach when you select the system configuration and their components. I would like to thank my colleagues for their contributions to the research. And this is the end of my presentation. Thank you for your attention. If you have any questions, feel free to email me at this email address. Thank you.
So we thank SCAPEAW Johan for his presentation. Our next speaker is Magnus Pihl from Micropower, and he will talk about silicon carbide in electric vehicle chargers, 5 years of field experience. The floor is yours.
Då ska vi se här. Okay, hello everybody. So my name is Magnus Pihl. I'm working as a technology lead at a company called Micropower. It's so that's the change. No? I turned off. I should have gone. Oh, sorry. So Micropower is a Swedish company. We've been around for quite a long time. We have been doing battery chargers since 1984, mainly for material handling, which means forklifts and other industrial products. We also started 4 years ago to do lithium batteries, and that is today about 50% of our turnover. Situated in Sweden, sales 100 million euro, 450 employees. So we know a lot about charging and batteries, but what about silicon carbide? I was here 5 years ago to present our transfer over from traditional Mosfet to silicon carbide. We had at that time last time buy of an existing Mosfet transistor, and we decided to go to silicon carbide. We really haven't researched that too much at that time. We spent about a year intensive lab and field tests, and then we start using them in production. And so what is now the result? It's actually very positive. We have soon used 500,000 components. We have shipped out 58,000 chargers as of today. And we are now at the 3rd generation of the transistor. We choose the Cascode transistor that Anup was presenting here earlier. This was of 2 reasons, really. One was that we didn't have to alter our gate drive, and the other was that we got a good price for it. And that combination is hard to beat. So, and we didn't really know this technology at the time, but we learned a lot during that year. And after 5 years, I would say it works very well. So we continued. So 2 years ago, we converted another charger over to silicon carbide. But not to put all eggs in one basket, we this time choose Mosfet, a SiC Mosfet, and a module. This was another power level, and we wanted to do the redesign from scratch. And since we are producing in Sweden and production cost is relatively high, labor cost is high, we save time by using a module compared with a discrete. The discrete is sure cheaper as a component, but if you take into account ceramic insulators, clips, assembly, etc., it's actually, we save money by using modules also at this very modest power level. The power was 8 kilowatt in this situation. So this is a 80 milliohm, 1200 volt module. And at the same time, we also changed the auxiliary supply over to silicon carbide. This is something for industrial use that is very important. You need to have your 40-50 watt of 12 volt or 24 volt for your fans and your control system. And here we changed from a 1500 volt MOSFET over to a silicon carbide. Same time we also changed from a hole mounted device over to a surface mounted device. And since we lowered the losses, we were able to cool the component just by the circuit board, so by having some extra copper surfaces on the PCB. So the overall system cost here also was lower. And here we actually have a lot of different suppliers for this type of components. So we have approved 3 or even 4 different brands of transistors and tested them. So it's now up to our purchase department to choose whatever component they want, which is very good right now with the component crisis. So we have shipped about 10,000 chargers of this style. And it's going well, I would say. So then what about quality? Actually, I don't have a figure. This is an estimate. The problem is that when you do your lab tests, you have 100 pieces, you test them, you measure them, and you get your result. We have shipped out 58,000 chargers globally, and we have 8 or 10 different repair workshops servicing our chargers, and our systems for feedback isn't perfect. So this is an estimate. By talking to the service workshops, we get about this number, and we're happy with that. So the message is this works very well. If we compare with before, when we have the MOSFETs, we have about half the failure rate. And the reason is probably mainly because we had 950 or 1000 volt MOSFETs, and with silicon carbide we were able to jump up to 1200 volts. So we got the withstand voltage is better. But then also we have IGBT chargers, and they are very similar. We don't see really any difference in quality between IGBTs and silicon carbide. Really, it's really hard to distinguish between component failures and location and local grid quality. We do have sometimes many failures, but then it turns out it was a lightning storm and every other equipment at that site was also damaged. So it's really, really hard to know. But overall, it's going very well. We're really, really happy with silicon carbide. As I said, we have had now many units out for 5 years, or the oldest have been out for a little over 5 years, and we cannot see any type of wear out on the components so far. The statistics shows that 5 years old units don't fail more than the new units. And now we promise our customers 10 years of lifetime minimum. So we're still only half through, but so far so good. So, and of course this is then mainly the JFETs, the Cascode has been running for 5 years, the Mosfet's been out for about 2 years, but the same with them, we don't really see, and of course 2 years is a very short time. One thing that someone has mentioned is EMC, and EMC is an issue. I would say we spend a third of our design time on EMC. And one drawback with the Cascode is that as was presented earlier here today, the switching time is more or less set by the internal gate resistor in the Cascode, and you cannot alter that as a user. So, as I said, we have changed, we are now at third generation of components from the same supplier, and when they change from one of the generations to another, they choose a gate resistor, and they test it, but they only test with an oscilloscope, so it all looked nice on the oscilloscope. When we put them in our product, we saw extensive oscillation at around 200 megahertz. And you really don't see that if you just measure in the time domain. And we couldn't really do anything. We tried to alter the gate resistor, nothing happened. So we have to go back to the supplier, and they agreed that they have to change the gate resistor, which is not that easy because that's down in the silicon. But they, after that, have also now started to release variants with different resistor values there, soft switching, fast switching, etc. So this is for sure a limitation of the Cascode, that you can't control the switching speed. But after they altered the resistor, it worked nice again, and we're happy. But that was another, it's a loop, so it takes a while to do that change. And of course, they cannot adapt to every customer. But we spend a lot of time on EMC, and also with the MOSFETs, we see that as we use the transistors, we switch at around 50 kilohertz. And we don't really see that switching losses is an issue. So very typically we slow down the silicon carbide transistors. We don't really see that we need much faster transistors. When we try to switch faster, immediately we see EMC problems. You can do better by making a better design, adapt the layout of everything, but I think they are as good as they need to be right now. We have problem to handle faster components. We heard earlier here that silicon carbide not always is the best solution, but I think for our products, so this range of chargers are all three-phase supplied, which means that the input voltage is from 380 to 480 or even 600 volt. And here there is no alternative to silicon carbide today. So right now we are phasing out IGBTs. This is an old charger that has been in production since 2015. We have shipped about 40,000 units. At that time, we had Mosfets and IGBTs. We wanted to use a module. The Mosfets didn't fit inside the module because they were too big, so we decided to go IGBT. We lowered the switching frequency to about 38 kilohertz. Still, we have excessive switching losses, but it was good enough. But now when we start to analyze, we took the same module as I showed earlier, an 80 milliohm SiC, and put in the charger. The cost difference is about €10 between this IGBT module and the SiC module. This is almost twice the price. We pay something between 10 and 15 euro for an IGBT module and 10 euro more for the SiC module. But we could immediately lower the heatsink cost by 2 euro, making it slightly lighter. And we reduce the losses with 140 watt, and this is more or less all switching losses, some conducting losses also. And if we look at the typical charger, typical charger operates over its lifespan, minimum, typical 30,000 hours. And we design for, and some customers use them, 60,000 hours. And that saves something between 4,000 and 8,000 kilowatt hours. So that is a good investment. And IGBTs really doesn't work. I heard the question before about customers paying for better efficiency. Typically not, but it's getting better. They want it for free, as typical. But there is also this time competition that sometimes you get paid for it, sometimes you actually throw out your competitors because you have better efficiency. And I don't think that, or I think that with now energy crisis, all other crises we have, energy efficiency is more and more important, and electric price will go up, etc. So we can't really see, we will throw out every IGBT we got in this type of DC-DC converters because they're old and obsolete. Another change we're doing right now is that we have Canada. I don't know if anyone is from Canada here. The grid is 600 volt, which is a bit problematic. The only country, I think, that got 600 volt as their standard three-phase voltage. We have today used 1200 volt IGBTs, same IGBT chip as the discrete version. Also lowered the switching speed. We're now looking into going up to 1700 volt to get a little more margin. 1200 volt components on a 600 volt grid is a bit on the edge. We see more failures there than in other countries. And also the old 3-pin TU247 is kind of crazy when you look at the creepage distances between the pins at that voltage level. So we're going over to a 4-pin component also in this change. The rest will be kept as it is. And we expect about, this is still in the planning, this is going to happen the second half of this year, but we expect about 2% higher efficiency when we go over to the silicon carbide on this charger also. Other changes we're doing right now is that we are trying with 0 volt off. This saves a little, it's not a big thing, but the fewer components you can have in your production, the fewer solar errors, etc., etc. And for sure, a 15-0 is easier to design than a plus 15 minus 5. So our latest product is having 0 volt. It's in test. We haven't delivered it yet, but we haven't seen any problems. We have measured a lot, and it looks good. The careful approach of this was that we choose a gate driver with a Miller clamp transistor, so that we first switch off with a resistor, and then when the gate voltage is 2 volt, there is another short circuit transistor that short circuit the gate down to 0. You have to be careful when you ship larger volumes. And this has been tested now for, and it's been a year in testing, and we have, as I said, not seen a single failure on this. So we're going to continue with this. The other big change, as I mentioned, is the 4-pin. First, we see a lot of new generations of transistors only coming out as 4 pins. And if you look at the design, the shortest creepage distance in the whole design is between the pins on the transistor. So that is one of the more critical points in the design. And the high voltage pin is in the center, and you get two creepage distances. So it's really, really a crazy design for high voltage applications. So the 4-pin makes so much more sense. So this is also something that's going to happen over the coming year. Then I will end my presentation with this. I think I showed this 5 years ago when I was here last time. But for you who have not been in the business so long, times are easy for designers. This is the roadmap of 20 years of high switch mode chargers at Micropower. We started off 20 years ago. The best transistor you could buy was 1 ohm, 800 volt. And then RDS on have been lowered and voltage have increased. And now you can buy TU247, this is all TU247. Now you can buy a TU247 at 20 milliohm and 1200 volt. So in 20 years, it's 45 times better on RDS on, and it's at 50% higher withstand voltage. So to be really honest, on the old product range we have, now the components are as good as we need. Actually, now in the old days, transistor really set the limit on the design. We built as big chargers as we could buy transistors. Now it's transformers and other passive components actually the challenge. You can just buy as much silicon you need. So it's a big shift. So why do we then need more development and more transistors? Well, this is the reason. There is now the electrification of everything. So from mainly doing, as I said, forklift chargers at maybe 5, 10, 15 kilowatt, we are now looking into high power charging, big batteries, high voltage batteries, etc. So there will be no end of development and no end of the need of new and better components. So that was my presentations. Maybe.
Thank you very much. So, any questions?
I have one related to your initial slide. Basically, you said that you have not reached the wear-out phase from your semiconductors.
Yeah.
So based on a lifetime model and mission profile, what would you expect them to have in terms of lifetime?
We expect them to be better than 10 years. So this is, we absolutely don't expect them to fail after 5 years, but sometimes there are unknown problems. But a charger is, typically we guarantee 10 years of operation for our chargers, more or less continuous operation. Some users are using 5 shifts around the clock. Chargers are not the cycling on battery chargers is not that bad because usually you charge for an hour or half an hour. So compared with drive systems where you run for 15 seconds and break for 15 seconds, so all our estimates is that they will last 10 years or more. But it's still good to see that it's working.
Okay, thank you.
Okay, we're slightly off the schedule. If you have a short question.
Here we have one.
What parameters do you use to monitor the health of your converter over a period of time?
So if semiconductors fails or?
Exactly.
Yeah, well, as I said, when they fail, they go to a local repair shop, which we have in US, Europe, to Australia, China, and they should feedback. But the quality of the feedback is not as good as you want it to be. So it's often hard to distinguish between someone who has actually violated or crashed the charger, or if it's a semiconductor breakdown. If there is things we're interested in, they send it back to us at R&D and we analyze it. But it's really hard to get the numbers. You get the feeling. I mean, also in a business, you understand if the failure rate is on a level that the customers can accept. But it's hard to get the perfect numbers. But we get back and analyze, and then we make statistics from our service centers.
Okay. So let us thank the speaker. So our final presentation will be made by Felix Steiner from IPE. He will talk about gallium arsenide power diodes and the challenges of packaging and handling such devices. The floor is yours.
So, thanks for the introduction. And let's see. So we'll start with why would you use gas or gallium arsenide, and then I will maybe give you a little of an explanation why you would use gas as compared to silicon carbide, and then we will go to the challenges of working with gallium arsenide. So why gallium arsenide? The main reason is it's quite cheap, and there are already high yield capabilities of producing gallium arsenide devices, because gallium arsenide is well established in high frequency application in communications and signal processing applications. The bandgap of gallium arsenide is only slightly higher than that of silicon, but a lot lower than of silicon carbide or gallium nitride. But it is a direct bandgap, which allows for very efficient trap generation and thus very low switching losses. And the high electron mobility allows for lower conduction losses than in silicon carbide usually. And also these parameters, especially the low conduction losses and the low switching losses, are less temperature dependent than in silicon carbide. And just some random values here. Which one is the? Probably. No, it doesn't matter. So the electrical breakdown field is nothing really special with gallium arsenide. The thermal conductivity is really sad compared to the other materials, and also the melting point is not really interesting, yet the usable temperature range is quite high, a lot higher than a lot of silicon, because of the low temperature dependency of the gallium arsenide. And then the electron saturation velocity is also nothing really special here, but we still have a very high current carrying capacity. As you see here on the right image, the left die is a 60 ampere silicon carbide die rated for 1200 watts, and the right one is a 1200 watt silicon carbide die for 50 ampere. So, where would you actually get these devices? There's a little company in Dresden, Germany, that produces these dies, and they also develop these devices themselves. And they have they have their own production capabilities in-house for LPE, and also a joint venture with Azure Space. And as such, they have very high production capabilities. So now to some gallium arsenide in application. Ian Mosley did some research on the efficiency and can you use gallium arsenide basically as drop-in replacement for silicon carbide. And here he used a phase-shifted full-bridge DC-DC converter and replaced the silicon carbide dies in the output rectifier with gallium arsenide dies. And we can see here there's also an active snubber to reduce the overvoltages. And by monitoring the snubber voltage, the snubber losses, you can differentiate between the switching losses and the conductive losses. And you can see that you get almost the same switching losses between gallium arsenide and silicon carbide, despite the inexisting reverse recovery in the silicon carbide, which you still have with gallium arsenide, but the junction capacitance is just so low with the gallium arsenide diodes that balances out a little. And the rest is basically compensated by the lower conduction losses. So in the end, you get more or less exactly the same performance in the end here with 8.2 kilowatt output power at the same efficiency. And in a second evaluation with an LLC converter, we can see a very similar result. With a LLC converter running at 10 kilowatts at 100 kilohertz, we see a loss in power difference, a difference in power loss of only 13 watts, where the gallium arsenide underperforms slightly. But the gallium diodes are at only 70% cost of that of the silicon carbide die. So you get a trade-off of minimal power losses, but a quite large cost reduction for the dies. So, but what's the problem? You get a quite high current carrying capacity. You get a nice power per cost, and also a good efficiency or comparable efficiency with silicon carbide. But then there's the thermal conductivity, and that's 3 times lower than that of silicon. And compared to SiC, it can't compare. And also the fracture toughness is also even worse than that of silicon. And that leads to the question of what will you do? The low fracture toughness, you would need to improve the die thickness to be able to handle the dies effectively, because you can't go with thinner dies really, so you would lower your yield and then destroy your cost advantage here. So you would go with thicker dies, but then the low thermal conductivity demands that you go with thinner dies to reduce the thermal resistance. And then you get conflicting goals, and what do? We heard that earlier, a few presentations earlier. You flip chip the die, and then you can conduct the heat that is mostly generated inside the junction, so at the top of the die more efficiently, and you don't have to conduct the heat through the entire die. And with the GaN devices earlier, the effect wasn't really that dramatic. When you have a really thick die with 350 micrometers and the low thermal conductivity of gallium arsenide, the effect is really dramatic. With a 60 watt power loss here, and we have on the left the flip chip device, silver sintered, and on the right side the conventionally mounted die. You get a temperature rise for the flip chip die of only 74 Kelvin, and on the normal operation you get over 100, you get 185 degrees rise, so that's severe difference here. And it also shows that you can actually cool the devices sufficiently if you just flip chip them. So then you try flip chipping these dies, And when you solder them, you get this problem with the passivation here, just sticking out a little and building a dam where the air can't escape from the air or any gases that come from soldering. Can't escape, and you get a horrendous amount of voids. So you need to vacuum solder these. I mean, most soldering is in vacuum, so that's not really that much of a problem for normal production processes. So let's go with vacuum soldering. But the other problem is also the unsupported area where there's no solder on the edges where the passivation is. So if you go with vacuum soldering, you get a really nice attachment, as we see on the left. And in the image on the middle, we can already see a little problem with gallium arsenide. The image on the right shows it in more detail. This is a gallium arsenide diode bonded with 500 micrometer wire with just normal standard factory parameters. And there you see a chip piece of gallium arsenide where the bond was. So gallium arsenide is extremely brittle, and you have to account for that with bonding. But if you do not, you see this die here on the top, which was bonded by a standard packager, just with the normal factory standard values, established values. And then all the red arrows indicate some sort of breakage inside the die. And that's, of course, that's not okay. So with some modifications to the parameters, you get still good bonds, but no breakage in the die. So that's also quite manageable problem here. But still, it's just wire bonding with now a few more but thinner wires, which is actually not that bad because you get a little less current density with the 5 times 400 micrometers as with the 3 times 500 from before. But wire bonding is still completely feasible if you pay attention to the problematic parts. Well, no. Okay. Yeah. Another very interesting part would be to actually use silver sintering to attach to these dies for the better cooling capabilities, of course, and also because the interconnect is in general more reliable than solder. And with the pressureless silver sintering, you could even sinter without applying pressure to the die, which would probably pose problems with the brittle gallium arsenide die. And the lower processing temperatures of usually around 200 degrees C yield lower residual stresses inside the die. But what you get is you get a paste squeeze out, because with pressureless pastes you work with wet pastes, where you press the die in, you get squeeze out, and then when you heat this up, the passivation starts expanding more than the paste CTE being around 20 to 30, and the passivation being at 40 to 60 or so ppm. So then you get this separation as on the right, where the diode gets separated from the sinter paste. So yeah, doesn't really work until now. Well, until now and until someone fixes this problem. So yeah, that's basically it. For an outlook, we would need to find a solution for the sintering problem, or just stay with soldering, but that's lame. Important would be the topside interconnect, which is quite problematic because of the high current carrying capacity of the gallium arsenide dies, which leads then to extremely high current densities in the bond wires, which is already a problem with the current densities in silicon carbide, where you get sometimes more bond wire liftoff due to the high currents. So topside sintering or soldering would be a very important thing here. And of course, we need to do further evaluation of the electrical performance of the gallium arsenide in actual applications compared to silicon carbide. Yeah. That's it.
Thank you very much. Do we have any questions?
I have one. So I'm here. Have you evaluated the H3TB performance of your flip chip layout?
Not yet, no.
Okay.
It's planned for this summer though.
So, another question? Okay, let us thank the speaker again. Thank you very much. This concludes this section, and I will now hand over to Per Ranstad, who will be giving us some news about awards.
So, let's go this way instead. So, for the second time, we shall now give out the Wide-Bandgap Power Center awards, annual awards. This is something we started up 2019, and since then, when we gave out the two first awards, and since then we have had a fairly long pandemic, so there has been 2 years where we didn't have the SCAPE to give out the awards, but now we are coming again. And this time we will give out the awards for 2020 and 2021. So we have 4 awardees to present. But the background is the Wide-Bandgap Power Center decided in 2018 to introduce these awards in order to promote, it's too far away, engineering and scientific work in the area of wide-bandgap power devices and their application. And we have two awards, one which is named the Best Thesis Award, aims for the best thesis in this area in Sweden for the year, and that is for thesis awards for master thesis or bachelor thesis. Then we have a second one which is named Young Professional Award, which is targeting young professionals, which could also includes PhD students and newly promoted doctors. And the price is 10K SA key for each of these, and the decision maker on this is the makers is board of the Wide-Bandgap Power Center. So, we have 4 awardees. 2 of them will be present here and 2 will not. The first award is the 2020 Best Thesis Award, which goes to Christian Al-Kassir for his thesis, SiC Mosfet Function in DC-DC Converter. Christian is not present, but we will hold up. Might be he is on remotely. So if I can get his diploma. So if you can see this, Christian, this is your diploma, and now we'll give you an applaud. To take it the right year. Yeah, that was no, but we are on 20. And the second award to be given out is the Young Professional Award for 2020, and it goes to Ole Christian Språ from Norway, and he's recently, or at least 1.5 years ago or so, become a doctor, and the title is Design and Optimization of an Auxiliary Power Supply with Medium Voltage Isolation using GaN HEMTs. Impressive work, 6.8 megahertz converter. Congratulations. And now we come into 2021. And here we have Farhan Akram with the Best Thesis Award, and another one who could make it to come here. The title is Gate Driver Solutions for High Power SMPS using Silicon Carbide MOSFETs. Congratulations. And last but not least, the 2021 Young Professional Award goes to Keo Jacobs from KTH with a thesis titled Silicon Carbide Based High Voltage Submodules for HVDC Voltage Source Converters. Congratulations, Keo. Keo is placed in Canada and couldn't come here because of a conflicting conference. So, that was almost all for this award ceremony, so to say. So next SCAPE, we hope there will be no pandemic, but a physical SCAPE like this one. And then I expect us to have 4 awardees next time as well, namely 2022 and 2023, and then we are in phase again. Thank you.